Let's look at an example of a base-driven acyl substitution reaction. And in this case, we're looking specifically at the hydrolysis of an ester. Just as a reminder on figuring out our product, when we look at this reaction, we want to see that we have a carboxylic acid derivative. And in particular, because we have an oxygen with an R group attached to the carbonyl, we have an ester. And so we'll identify that oxygen and the R group attached to it as our leaving group. And we identify hydroxide as our nucleophile. Remember, with the sodium there, it's basically to tell us that the O of hydroxide is negative, and that's going to be our nucleophile. So in our product, we expect to see an alcohol is what the leaving group ends up as. And we expect our carbonyl to form a carboxylic acid. So we'll still have this methyl group present, of course, in the product. However, in this case, because we're in basic conditions, we expect that we're not going to have a carboxylic acid, which of course is an acid, but that we're going to see a carboxylate instead. And we'll see that as the sodium salt, since sodium is our cation that's present. In terms of mechanism, we're in base, which means that we can actually start with our carboxylic acid derivative. And we don't need to protonate our carbonyl. In fact, we don't want to protonate our carbonyl because if we did, we would have an O plus in base. We say no O minus in acid. We also say no O plus in base. So we're going to go straight to the first key step in acyl substitution, which is that nucleophile attaches, pi bond breaks. That gives us our tetrahedral intermediate. We have an oxygen anion. We have an OH newly added that will be our carboxylic acid, one of our carboxylic acid oxygens. And we still have our methyl group. Now at this point, remember that our alcohol portion of the ester is our leaving group. Normally we would protonate that to make it a good leaving group. In this case, we don't need to. And in fact, again, we don't want to, because if we protonate it, it's going to be positive and no O plus in base. So instead, we just go straight to the second key step in acyl substitution, which is that pi bond reforms, leaving group leaves. Now, on the one hand, we've been taught that an O minus is a poor leaving group, right? We usually think of that as something that we don't want to form, and in fact, we go through efforts in most of our mechanisms to avoid forming that O minus because it's not very stable and it's strongly basic. It's not very stable because it's strongly basic. Well, we're in strong base, so it's okay to have O minuses around. And in fact, if we think about this key step where our tetrahedral intermediate reacts, we're reforming our pi bond, kicking out our leaving group. We're trading one O minus for another. So we aren't really introducing extra stability or extra instability because of that O minus. Now, what we do have present, however, is our carboxylic acid in its acid form, and that's simply not going to last in base. So we need to get rid of this hydrogen. The other thing that we want to do is to protonate our alcohol, which is going to end up having that extra hydrogen. Alcohols are strongly basic. We are in strong base, so it's realistic that we'd have some O minus here, but we're going to assume, for the sake of argument, because the equilibrium is going to favor, particularly with a lot of water around, is going to favor protonation of that oxygen. So we're going to go ahead and do that. We can actually accomplish both of those in the same step with the alkoxide anion grabbing the hydrogen from the carboxylic acid. This will give us both the carboxylate and the neutral alcohol. Now we're tempted to want to draw some mechanism arrow that brings the sodium in, but remember we don't use mechanism arrows for ionic bonds, and so the two will stick together simply by rights of being oppositely charged.